Terve, mä oon Haapalan Eero, Liikuntalääketieteen yliopistonlehtori Liikuntatieteellisestä tiedekunnasta ja tänään mä vierailen Matematiis-luonnontieteellisen tiedekunnan eri laitosten tutkimusryhmissä ja tutustun heidän tekemäänsä tutkimukseen. Ensimmäisenä lähdetään tutustumaan matematiikan tutkimukseen.
So I think one special feature of mathematics is really the earnings of mathematics, that if you prove something in mathematics, then it will remain true always. And that's why the applications can come a lot later. If you prove something like, for example, the things that the Greeks proved, they are outdated at all. They are old mathematics. They are as beautiful theories as they were 2,000 years ago. Like I suppose probably you have heard about Pythagorean theorem in school. That's a perfectly fine piece of mathematics either together, which has a lot of applications.
There was someone called Sven Mandelbrot who sort of invented the field of brachiometry in a way, in one of his famous quotes was clouds are all spheres. So he wants to push the idea that a lot of real world will have these intricate structures, and that maybe a different mathematical idealization that's not based on very simple geometric tricks might be better to capture the essence of some of these real world objects.
Well, that's a beautiful example. The Roman is the broccoli. So also this is also exhibits the notion in fractal geometry, which is very common, something called self-similarity. So it looks like a similar copy of itself with many different scales and locations, and then zoom into the property, and then you see the same function again. Zoom more, you can see the same property again. And once again, it's something which has dimension higher than 2, but less than 3. Something between 2 and 3 dimension.
You want to find like a relatively small set of rules which somehow produce something rather complicated. Self-similarity somehow only requires a relatively small set of rules, which is some sort of like self-referential reproduction. Right? So, I mean, this is how like class work, right? Like a tree doesn't think, oh, I'm going to build this beautiful fractal structure, right? A tree just thinks, I'm going to grow, and once I hit a certain width, maybe I offshoot and I split, right? And this idea of this like self-referential, like grow and then split, and then grow and then split. This recursive process creates these types of structures. So the number of rules that you need in order to build something like this is relatively small, yet the objects that you get like are complicated or have these weird properties. So I think one idea that somebody like me or somebody who does a pure mathematics for the perspective of fractal geometry is like finding this like very simple assumptions that kind of produce these objects. Like what is the simplest way that we can produce these objects, and what can you say about them given this model for how they appear? Yes.
But I should emphasize that mathematics is not rocket science. Yeah, so I think this is very true. So I think mathematics is every bit as hard as rocket science, but we don't build rockets. The current nowadays is a good way to study mathematics.
One application of this fractal or house of dimensions is it gives a way to compare two objects which might be very different to compare otherwise. Like if you take two of his Procomis or two beds of Johann Marx or two coastlines of different countries, then how can you say that which one is bigger? Or you have a large set of these objects, can you point out one of them that is much more different than the others? For example, in some medical studies it has been found that the human lungs often have fractal dimension about 1.6, no matter of the age or height or this kind of qualities of the person. But in some cases, some diseases of the lung can affect the fractal dimension.
Like we had no data, we don't know lab work, and very rarely our research involves computers. So then usually the question, so what do you do? we cut to this room and we just talk and write in the blackboard, and then we stare for a long time on the blackboard. Your puzzles we know to the next. So it's a very peculiar experience, but I think it's quite unique to the research you have.
Nyt lähdetään tutustumaan bio- ja ympäristötieteiden laitoksen tutkimustoimintaan.
Niin, eli tämä tavallaan, missä me nyt käytiin, oli yksi näistä meidän pöntöistä, mikä on tässä Jyväskylän ympäristössä. Niitä on 400. Eli silloin mä tulin tänne 4,5 vuotta sitten Turusta ja perustin tämän pönttöpopulaation. missä me käytiin. Ja tavallaan se tausta-ajatus siinä on, että me halutaan tutkia, miten luonnonvaraiset eläimet reagoi ympäristön muutoksiin. Tässä tapauksessa, mitä me tänään tehtiin, niin siinä tutkittiin sitä niin kuin kasvien toksiinien vaikutuksia niihin ja vaikuttaako ne suolistomikrobiomiin. Eli ne oli 7-päiväikäisiä poikasia ja niitä on niin kuin seurattu, että me tiedetään, milloin ne poikaset kuoriutuu. Ja sitten on tietysti tarkkaa se, että sinne ei voi mennä milloin vaan ja kuka vaan esimerkiksi jos ne menisi liian aikaisin, se emu voisi hylätä ne poikaset. Eli me tiedetään, että 7-päiväisiltä ikäisiltä poikasilta me voidaan mitata ja se emu ei hylkää. Eli ensin mentiin sinne pesälle ja tarkistettiin tietysti siellä, että siellä pesässä on kaikki ok. Siellä on joskus ollut esimerkiksi kyy, eli ei mennä sinne pesään niin kuin kädellä näin. Ja sitten ne kerättiin ne poikaset semmoiseen lämmitettyyn astiaan, koska ne on tosi pieniä vielä, ne ei pysty niin kuin lämmön säätelemään kunnolla itseensä, ei joudu niitä höyheneen vielä. Ja sitten ensimmäinen on rengastus, eli niillä annetaan yksilöllinen tunnus, joka on tällainen vähän kukrainen rengas. Ne rekat on luonnontieteelliseltä keskusmuseolta, eli ne on niin kuin säädelty, että kuka saa rengastaa, pitää olla rengastuslupa. Ja kaikkien näihin muihinkin pitää olla toki lupa. Sitten oli ne mitat, eli perusmitat oli siiven pituus ja paino, jonka kertoo sitä kehityksestä, että siellä on joskus on vahnanpohjimmaisia siellä pesässä, jotka on tosi pieniä ja ne ei ole vaan saanut riittävästi yleensä ruokaa, että emo ei välttämättä pysty ruokkiin kaikkien samalla tavalla. Sitten meillä oli se ulosnäytteenotto, jossain oli semmoinen poop is gold, niin eli siitä selvitetään ne suolistomikrobit, niin kuin ihmisilläkin, niin sen voi selvittää myös linnuilta. Ja ne on tosi, niin kuin, sanotaanko näin, että ei niitä oikeastaan vielä tiedä, kuinka tärkeitä ne on, tai niin kuin mihin kaikkeen suolistomikrobiomi vaikuttaa samalla lailla kuin ihmisillä, niin sitten niin kuin luonnonvaraisilla eläimillä. Luultavasti käytännössä kaikkeen mahdolliseen. Että jos ihmisillä on löydetty, että tosi moniin sairauksiin ja mielenterveysongelmiinkin, niin on luonnonvaraisillakin eläimillä löydetty. Että esimerkiksi me havaittiin, että lämmönsäätelykykyyn ja immuunivasteeseen vaikuttaa ne mikrobit. Ja sitten oli verinäytteenotto sitä DNAta varten. Eli se oli tästä vähän niin kuin ihmiselläkin, se oli tästä siipisuonesta sellainen pieni yksi pisara verta riittää siihen sterilillä neulalla ja siihen lasikapilaarin keräten. Varmaan samoja kapilaareja kuin ihmisillä käytetään sormenpäänäytteissä. Eli aika samoja. Ja sitten oli vielä se annostus, eli tästä kun me haluttiin tutkia sen kasvitoksiinin vaikutusta ja erityisesti vaikutuksia suolistomikrobioon, niin sitten annustellaan niille se. Eli se on niin kuin koeasetelma, missä on tietyt ryhmät ja sitten vertaillaan niiden vaikutuksia kasvuun ja fysiologiaan ja sitten käyttäytymiseen. Perustutkimus on tietysti semmoista, että ymmärretään paremmin, miten asiat toimii. Että mun sanoisin, että siitä asti kun on opiskellut, niin tavallaan se ajatus on, että haluaa ymmärtää, miksi, niin kuin tavallaan, miten asiat toimii, miksi ne on niin kuin ne on ja miten asiat liittyy toisiinsa. Mutta tavallaan soveltava aspekti on se, että miten ympäristön muutokset sit oikeasti voi pitkällä aikavälillä johtaa niin kuin vaikka liittukantojen niin kuin vähenemiseen ja miten niitä voitaisiin sitten estää. Ja sitten toinen on se, että löydetään semmoisia biomarkkereita, että ennen kuin ne populaatiot, vaikka linnut, niin kuin vähenee, niin havaitaan, että okei, tämä markkeri on koholla, tässä on niin kuin riski tavallaan, että jotain on meneillään, mitä me ei vielä ymmärretä. Sitä myös, että löydetään niitä biomarkkereita.
Ja seuraavana vuorossa onkin sitten fysiikan laitoksen kiihdytin laboratorio.
Mä oon säteilyturvallisuusvastaavana täällä ja hoidan näitä dosimetrihommia ihmisille, jotka tulee tuonne kiihdytinlatan puolelle töihin. Ja vaikka sä nyt oot vain pari tuntia, niin laitetaan silti tämmönen dosimetri, joka mittaa säteilyannoksen, joka osuu suhun siellä mahdollisesti.
Today we start in Eurogam. So we are Eurogam, and Eurogam is a sphere of germanium detectors. We use them to see radiation of reactions that we are and experiments we're trying to do here in our laboratory. So in it, the beam in a typical experiment, the beam comes from one side and it hits a target inside the target chamber. And then when that happens, we create all kinds of products. And these have all been registered in a chart like this. So everything that has been created, all the black ones are the ones that you find in nature normally. And then all the other ones we have to create by ourselves in a laboratory like this. And to really understand all the qualities of these radioactive isotopes, we call these isotopes, we need a laboratory like this. With EuroGAM specifically, we can look into what we call the excited states of these isotopes, and with it we can investigate the structure of these isotopes. And that can be helpful for all kinds of different fields such as astronomy, or I suppose just to kind of see the fundamentals of nuclear physics. And to do, before such an experiment, what we need to do is we need to calibrate such a device and make the device work as well as possible as we can. And to do that, we typically, before an experiment, we put in some of a calibration source and then go from there to see the qualities of the detector and how to optimize it as much as possible. So first we will start by getting the source from the source safe, a European barium source. So these are also on this chart somewhere. And they give off a certain amount of light, and just like normal reactions, but we know these lights. And then we put that in a EuroGAM, we see if we see that light, and we see how we can optimize the kind of the peaks there. And after that, so after we've gotten it, we open up EuroGAM, we put it in, we close up EuroGAM again, and then we can go to the computer and see how these peaks look. Our research is quite fundamental in nature, so we really try to get like so there are a lot of radiational applications. You have radioactive techniques in medical services, and you have nuclear reactors for energy, and that's all very important. That resides on a certain amount of fundamental knowledge that we have, and here we try to really gain the fundamental knowledge. For example, to it can be used to aid these kinds of services, but also we try to aid other fields like astronomy. Astronomy requires a lot of knowledge about this part of the chart, and how to produce that part of the chart, for example, is something that you can investigate here. And this together, like I think research is really a step stool for all these other fields to flourish in that sense.
Even within our field, I mean, I suppose in nuclear physics is a source of answering some very big questions. So some questions such as, why are we here? Why is there more matter than antimatter in the universe? That's why the universe even exists. So basically matter is everything in the universe. Antimatter is its opposite. And there's much, much, much more matter than antimatter in the universe. The calculations suggest that there should be an equal amount of matter and antimatter. And it's a very big question as to why matter won over antimatter, because when they meet, they explode. So this is a very big question, and some of the work we do here can relate to questions about that. And from that, we maybe study the shape of a nucleus, and there's certain shapes of nuclei. So a nucleus isn't always just a sphere of particles. It can be pear-shaped, it can be rugby ball-shaped, and if it's pear-shaped, it kind of potentially inform us as to very important information about why there's more matter than antimatter in the universe. This is very, very important.
If you think about the common people like me, not in the nuclear physics, where I can see the products of nuclear physics, what you do.
So we have there's a fission reactors, but we also have the upcoming fusion reactors. So these are very impressive ways to make a lot more energy, a lot cleaner, not using uranium, but using hydrogen. That's all nuclear physics.
When you travel and you go through an airport and you need to have your luggage scanned, this is another place. You use X-rays to tell what's in your luggage, make sure you have anything you're not meant to have. Even in the sky, the stars themselves are nuclear reactors.
That's right.
So they're everywhere, really. The stars are very important because that's where all these heavy elements have come from. And, they say people are made of stardust, I suppose. Then this is true. A lot of the elements in our body, I think all of them really are from different interactions and reactions within stars. So when stars explode, they create some very, very exotic nuclei, and they're inside of us all, inside wedding rings, and inside the gold in a wedding ring comes from a star, from different reactions and stars. So these things are very important, and it really is everywhere.
Nyt ollaan kemian laitoksella ja seuraavana tutustutaan orgaaniseen kemiaan.
Okay, so what we're trying to do is basically textile, but with molecules. So there is already some evidence, like materials like polymers get entangled, like pasta, basically. And the more they get entangled, the more it changes their properties, mechanical properties, the way they stretch, the way they resist shocks and other properties like this. And so the problem with this is that these entanglements in molecules, they don't form in a controlled way. They just form at random. And so it's very difficult to actually evaluate what is the effect of entanglements on all these mechanical properties. And so the idea of what we're doing in the lab is that we are trying to learn a recipe on how to make knots with molecules. First, a tiny knot of the size of one molecule, and then bigger knots of the size of polymers. And then this way, if we really control how to form knots with these polymers, then we can understand how this changes the mechanical properties and tune this mechanical property accordingly. And so for now, we are at the very early stage of this research. And what we're trying to do is take molecules, relatively simple, relatively short molecules, and see if we can control the way we can braid them to form this helices with either one molecule, two or three molecules forming a helix around each other. And then we're trying to connect these helices into different structures to form different types of knots, which are smaller and bigger. And in the future, what we're hoping for is to form knots which are bigger and bigger, and eventually completely knotted materials. And then we will be able to evaluate really what is the potential of this type of knotted molecules for real applications. But we are very far for this as of now. So for now, not much is known about this knotted molecule, so it is kind of difficult to project ourselves. Of course, when something is new, you always think that it has potential somewhere, and then it happens that after 30 years it has. Actually, you develop completely different applications from what you thought about. But what is thought of currently is that the biggest application will be in the field of materials, because it is already known that the presence of knots affects the formation of materials and their properties. And so we could imagine, for example, new materials that would be better stretchable. So all the materials for now, which are brittle, for example, it's because when there is a stress, they cannot handle much the stress. So the energy of the stress is localized somewhere, and then that breaks the material. And of course, you cannot reuse it several times once you have work on it. But then when they are knots, all the different polymers can slide in the knot quite freely. And so when you apply a stress, the energy gets diffused into the knots. All the thread just move around. This diffuses the energy. And so it's expected that it would be less brittle, more robust. You could reuse these materials many more times. And so that's one of the applications that people are thinking of. Lots of molecules which are forming our body, in our cells, like proteins and DNAs, they actually have knots. And it's poorly understood how they form, why they are there. It seems that they exist for a reason, because they're always there, but it's very difficult to pinpoint why they are there. And so from a fundamental perspective, this type of technology we are developing is also helping us to understand what's happening in nature using a synthetic model. Knots are everywhere. Like shoelaces. When we go rock climbing, we use knots everywhere. In fact, they are so much everywhere that we don't really notice them and how important they are in our lives every day. And so the assumption underlying a research is that even though it doesn't have any application right now,
it must be also useful in some sense to tie knots with molecules. But of course, it's difficult to know what they can be useful for before you manage to make them.